Democritus was the first person to believe that matter was made of atoms. He said that atoms were indestructible and indivisible. Democritus also said that atoms move through empty space and have different shapes and sizes. He was just a philosopher, so he didn't do any experimenting, but he really was the catalyst in the idea of the atom. In the case of the atom, Aristotle rejected every idea that Democritus has ever had. He believed that there was no possible way that there was an atom or there was empty space that they moved through. He believed that all matter was made from earth, fire, air, and water. There being no way for either Democritus or Aristotle to prove their very different ideas, there were two theories about the atom. But Aristotle, being the man that he was during his time, won the popularity contest, and his ideas were accepted while Democritus's ideas got rejected. Then came Lavoisier. Lavoisier revived the ideas of Democritus. He was setting the idea that matter was made of atoms, and there was no way that atoms were made of earth, fire, air, and water. In his experimenting, he found the element oxygen. After finding this, he concluded that matter was made of elements which were further made of atoms. Following his discovery of oxygen, he conducted even more experiments that led him to make the first ever list of elements. Another conclusion that Lavoisier made was that mass was not created nor destroyed.
Dalton generally agreed with Democritus's theories. Dalton was actually able to perform experiments to test his hypotheses. He summarized his findings in Dalton's atomic theory in 1803. Dalton's atomic theory states that matter is composed of atoms, which are indivisible and indestructible. Atoms of one element are all similar in size, mass, and chemical properties, which are different from those of any other element. In chemical reactions, atoms are separated, combined, or rearranged, and atoms combine in whole number ratios to form compounds. These findings combined form the atomic model Dalton came up with, the indivisible solid sphere model.
Thomson contributed to the atom by finding that atoms are divisible and have subatomic particles. In 1897, Thomson began his cathode ray experiment with the cathode ray made by Sir William Crookes. From the findings of Crookes, Thomson already knew that the electricity in the form of radiation moved from the anode to the cathode end. Crookes also found that the radiation in the cathode tube produced a green light, which came to be called the cathode ray. Soon the electron came to be found by understanding that changing the metal made up by electrodes and varying the gas pressure didn't affect the cathode ray, which meant the ray's negative particles were found in all forms of matter. Thomson, knowing that the cathode ray were streams of negative particles and the negative particles carrying an unknown value charge, began to find the mass and charge of the electron. First, Thomson made a new cathode ray model with magnets and electric plates with opposite charges, and he found that the cathode ray was deflected to the positive side. Knowing that opposites attract, he proved electrons to have a negative charge. He then changed the force of the magnetic and electric fields of the cathode ray and compared that in a charge to mass ratio, which he then compared to other known ratios. He found that the mass was much smaller than the lightest known atom, hydrogen. This proved that there were smaller particles in atoms.
When the electron was found, some of its properties caused some interesting questions about the nature of atoms. It was understood that matter was neutral and that it had no electric charge. One of his questions was, if the mass of an electron is so small, what accounts for the rest of the mass in a typical atom? J.J. Thomson wanted to answer these questions. He proposed a model of an atom that became known as the plum pudding model. The model consisted of a spherically shaped atom composed of a uniformly distributed positive charge, which was the pudding, where the individual negatively charged electrons resided, which were the plums in the pudding.
Robert Millikan was an American physicist from 1868 to 1953. He helped form the atom by determining the charge of the electron using the oil drop apparatus. First, the oil is sprayed from the atomizer. These oil droplets then fall through the hole in the positively charged plate. The source of radiation then knocks the electrons out of the air, and they stick to the oil, giving the oil a negative charge. Millikan could see all of this through his microscope by varying the electric force. Seeing that the rate at which the droplets fall and the gravitational force, Millikan was able to find the mass of the oil droplet. With the mass, he was able to change the charges of the plates and almost made the atom float. Using all of this information, he came to the conclusion that electrons carry a -1 charge. After he found the charge, he then also used the charge to mass ratio to find the mass of an electron to be 9.1 times 10 to the 28 grams. Ernest Rutherford was a physicist from 1871 to 1937. In 1911, he found the nucleus and protons through his gold foil experiment. He began to study how alpha particles, radioactive particles, interact with matter. Rutherford set up a lead block containing a projector of alpha particles pointed at a gold foil sheet. Because Rutherford was aware of Thomson's plum pudding model, he expected the alpha particles to only move paths slightly if next to an electron, but in this case, that's not what happened. As Rutherford shot these alpha particles at the gold foil, he noticed some alpha particles pass through with no deflection. Some passed through with slight deflection, and some alpha particles didn't pass through and were deflected back. Rutherford proved the plum pudding model wrong with his nuclear model, stating that an atom consisted of mostly empty space. The atom's positive charge and almost all of its mass was located in a dense region in the center of the atom called the nucleus, as well as the electrons were held within the atom by their attraction to the positively charged nucleus. Rutherford then concluded that the positive charge of the nucleus deflected the alpha particles because same charges repel. When the alpha particles came close to an electron or the nucleus, they were deflected slightly, but when the alpha particles directly hit the nucleus, they were deflected at a large angle. However, Rutherford's model didn't account for all the atom's mass. By 1920, he refined his concept and decided that the nucleus contained positive charged particles with a 1 plus charge, and it had equal mass of an electron. He called this a proton.
Bohr found that there are limits to how much energy atoms, hydrogen atoms in particular, can have. His atomic model was the planetary or solar system model. In the model, electrons moved around the nucleus in certain circular orbital paths, much like the planets in our solar system. To quantify the orbits of the electrons to better study them, Bohr gave quantum numbers to each orbital path. The lowest state of energy allowed is called ground state and is located right next to the nucleus with a quantum number of n equals 1. The higher the quantum number, the more excited the electrons are, the more energy they contain, and the bigger the orbit. When electrons gain energy from an outside source, they move from a lower energy orbit to a higher energy orbit, and vice versa. When electrons lose quantum value, they release energy in the form of light, also known as photons.
De Broglie put together that Bohr's quantized electron orbits had characteristics that were very similar with waves. For example, only multiples of half wavelengths are possible with a plucked harp string because the string is fixed at both ends. De Broglie also saw that only odd numbers of wavelengths are allowed in a circular orbit of fixed radius. Due to these thoughts, de Broglie began to wonder if particles of matter, including electrons, could behave like waves also. He eventually came up with an equation that predicts that all moving particles have wave characteristics. Chadwick lived from 1891 to 1974. He bounced off of Rutherford's findings to discover that the nucleus contained another subatomic neutral particle that was called a neutron. A neutron is a subatomic particle that has a mass nearly equal to a proton, but it carries no electric charge. In 1930, it was discovered that beryllium, when bombarded by alpha particles, emitted a very energetic stream of radiation. This stream was originally thought to be gamma radiation. Eventually, Chadwick discovered that putting up paraffin wax directly after the beryllium caused protons to shoot out. He just didn't know what was coming off of the beryllium. He only knew that it had to be something with no charge. Chadwick then discovered these to be neutrons.
Erwin Schrödinger was an Austrian physicist who developed the quantum mechanical model of the atom, which built off of de Broglie's wave particle theory in that it treated electrons as waves. It was also similar to Bohr's model, except it worked for all atoms, not just hydrogen. Both his and Bohr's models limited the energy of electrons, but Schrödinger's model didn't describe the path of the electrons at all. In addition, Schrödinger developed the Schrödinger wave equation, which was used to find the probability of finding electrons in specific spaces around the nucleus. The solution to the wave equation is called the wave function, which predicts a three-dimensional volume around the nucleus, or an atomic orbital. The orbital is like a cloud around the nucleus containing different densities. In the cloud, the higher the density, the more likely it is to find an electron in that space, and the lower the density, the less likely.
As you can see, many of these scientists and their studies contributed to the history of the atom to form the atom that we know today.